This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Today it is my great pleasure to welcome Franziska Knolle, who is coming all the way from Germany. She arrived here yesterday, and I don't think she quite knew how the jet lag could be so brutal.
How bad it could be.
It could be. So yeah, thank you so much for coming all the way to present to us. So a little introduction. So Franziska is a group leader at the Department of Neuroradiology at the Technical University of Munich in Germany, and a former Marie Curie Fellow. She did her PhD at the Max-Planck in Leipzig, and postdocs at the University of Cambridge. Today she will be talking to us about predictive coding ideas in psychosis applied to language, and so I'm very looking forward to your talk.
Thank you, Marta. Thank you for the nice introduction, and thanks to you for coming. So basically the goal of this, of the couple of projects I'm going to present to you today, was to look into how the prior weight, which is basically how much you rely on your prior beliefs compared to sensory evidence, changes when we look at different stages of psychosis. But before I'm going to actually talk about that, I want to... It did work before. Here we are. I want to show you an example. So the audio is not super loud, so you need to listen to what I'm playing to you today, or now. So just be careful now. So playing that again to you. Did you hear anything?
A gunshot?
Sorry?
Is that a gunshot?
Not quite. So it was a word that I presented to you. I will go back and present it again to you because I think it's the volume the issue.
Okay.
And just try to understand which word I'm presenting to you. And again. So now I'm going to give you some context.
Have you heard about the open?
Do you now hear the word that I presented? Oh, funny. That must be the volume. So again, the context. So usually it's a very clear effect.
Have you heard about the open?
I hear professor, but I don't think it is because it doesn't.
So the word is position. Have you heard about the open position? So wait, now that you know, now that I gave you the word, maybe it works like this. So now listen again. Can you hear it? Oh, maybe it works later on. So usually, when I play that at conferences, it works really well. And people are like, oh my God, in this kind of gunshot, you suddenly hear a word very clearly. And usually...
Because there is a joke board at conferences usually.
Yeah, maybe it's the pragmatic context as well that shapes your prior. So usually that is a quite nice introduction to give an example for predictive processing. So I'm sure that most of you are familiar with the predictive coding framework. So just a very brief summary. So what we assume is that our brain uses prior knowledge to infer causes of incoming sensory evidence. That is because usually our sensory input that we're perceiving is highly ambiguous and noisy. And in order to make sense of that, we're relying on these predictive models or patterns that we have. And so what it basically does is that we have this prior here. This is basically our prior belief, and this is combined with our input, which can be described as a likelihood, as a sensory likelihood, simply because it might be differently reliable in certain circumstances. And then what we get is a posterior distribution. And what I showed you just now, if it had worked, would have been that since the sensory input was highly degraded in this gunshot that you heard, the posterior moves very much towards the prior. So basically we're hearing what we're expecting. And that is what you would see here. So in psychosis, there is a couple of different types of evidence that this process seems altered. So this is here more from the reinforcement learning field, which can be related to predictive coding as well. And we see strong alterations in prediction errors. And so a prediction error is this very crucial element here, which is basically used to update our models. And we see that alterations, especially in the basic ganglia and the midbrain, are altered. However, if we think about this prediction error here, we can't really differentiate whether it is the prior or the sensory that is the sensory likelihood that is altered in order to have that altered weighted prediction error. So there is a large body of studies and evidence looking into exactly which part is the problem in the whole process, so whether it is relying on the prior knowledge, the prior beliefs, or whether it is the sensory evidence that is the sensory evidence which is a problem. So here's a study that looks into multimodal processing and basically found that there is an over-reliance on cognitive priors in early stages of psychosis. And this is basically a study that kind of finds exactly the opposite. So basically finds that the sensory weighting is different in psychosis. In order then to reconcile these different findings, what has been proposed is basically a hierarchical processing or a hierarchical predictive coding account. And the assumption of that is that we find an overweighting of sensory data at lower processing levels, which relates to delusions, and an overweighting of prior knowledge in higher processing areas, which could potentially explain hallucinations. And if you think about these two aspects down here, then what becomes highly crucial is that we have very clear definitions of these hierarchies in order to actually differentiate these processes. And that was one of our motivations of why we moved to language processing, because language is intrinsically predictive. You would have seen that in the first example, but you can also see that in sentences like this. So she likes her coffee with milk and sugar, exactly. And you would be highly surprised if I said the word lemon, for example. Language is also nice because it covers these different hierarchies. So you can look at it at a very low-level hierarchy, so when you look at phonetics and phonology, but also high-level hierarchies, such as pragmatics or semantics. And then, for me, crucially important is that language production and perception is altered in schizophrenia, and that it also is highly important when you look at the different symptoms. So, for example, in auditory verbal hallucinations, it is exactly the language with which it is conveyed, which with the hallucinations are conveyed. So we came up with a predictive language paradigm, which I will now walk you through in detail. And if you have any questions, please just ask right away. And we set up this paradigm in order to basically reflect this predictive coding process. And I will now go through each element and link you to the different aspects of the model. So first, when the people are doing this experiment, they're presented with a semantic prior. This semantic prior is a whole sentence up to the sentence final word. And this is basically a measure of predictability. And predictability is estimated using the concept of entropy. And here we have, it's basically a continuum. So we have the whole range of entropy covered from low to high. And a low entropy sentence would be this one.
The ship disappeared into the thick.
And it would be fog. So here, very few possibilities can be chosen in order to complete that sentence. And then high entropy, so low predictability, would be, for example, this sentence.
The new laptop was on top of that.
So this semantic prior very nicely links to our prior in the predictive coding concept. And it can be estimated in this paradigm. Then we have the sensory evidence. The sensory evidence is a very nice measure here because it consists of two aspects. So on the one hand, it consists of the sensory noise. So it's a sensory degradation of our sentence final word, and here we use noise recoding. So we basically presented the target word with different numbers of channels. Fewer channels would be much more noisy, more channels would be less noisy. So here are some examples. We have 4 different degradations. So this is the lowest, or so the most unclear, not understandable at all. Then we have 3 channels, also only understandable if you have some context. So now it becomes more clear. Did anybody get that yet? And then that's the clearest. It's the word box. So this is basically the ending to this unpredictable sentence that I played to you before. The laptop was lying on the box. So we have this sensory noise degradation level, but also we manipulate the amount of surprisal. So how likely a word is supposed to be appearing in the sentence. Because you can either have a sentence like the first one, she likes her coffee with milk, and you could say sugar, that would be a highly expected word, but you could also say lemon, it would semantically be totally fine, but highly unexpected. So this is the amount of surprisal that has also been manipulated. So for these high surprisal conditions, we use sentences like this.
The knight needed oil for his
joints. And then I'm saying joints instead of armor. So you would expect the word armor, but it is the word joints that I'm presenting.
Yeah, just a question about the manipulation of the prior. Were sentences always new, or did they learn over the course of the experiment that this was a likely combination?
So they were listening to 200 sentences, and they were all entirely new.
Mm-hmm.
So there is no actual learning possible in the task, only kind of an habituation to understanding these degradations a bit better. So you do get used to it, and after a while of being exposed to these low channel number degradations, then you are much better. You're getting much better in deciphering them. But other than that, there's no learning. So this sensory evidence links really nicely to the likelihood, the sensory likelihood that we have in our paradigm, then or in our predictive coding theory. Then we have the clarity rating, which is the first subjective score that we have in this experiment. And here, this is nice because it basically combines. So clarity, obviously your clarity rating depends on how noisy the input is that you're perceiving. So you will definitely rate clarity higher if something is more clear. But at the same time, you rate something higher in clarity when the sentence was predictable. Because whenever something is predictable and you have a very clear expectation of what is coming next, you also automatically perceive this word a bit more clearly. So this clarity rating basically gives us something like the precision of our prior and the likelihood at the same time. Then we have our posterior recording. So here we basically ask the participants, what did they hear? And this is a quite nice and direct measure of the posterior. And lastly, we have the confidence rating, which I haven't included in the analysis or the model yet because people seem to have a few problems with answering to the confidence, but we had expected the confidence rating to reflect the precision of our posterior. Okay, so now we basically saw that our paradigm in itself is already a quite nice representation of this predictive coding process. And then we didn't stop there, but we basically, together with Chris Mattis from Aarhus University, came up with a computational model to basically mechanistically describe the prior weight used based on a belief updating model. And what I'm showing you here is basically the linear relationships that we assumed between our parameters that we can modulate in our paradigm and the prior weight. So what these linear relationships reflect is basically that when entropy goes up, so predictability goes down, we're expecting our prior weight to move towards the sensory and away from the prior belief. And this is basically what we expect for all three of them. And what you can see here is that we're kind of expecting the same relationship on the clarity rating. And because, as I explained before, the clarity rating basically combines the precision of the prior and the sensory, we wanted to control our prior nu for exactly this variable. So we stratified our prior weight for this clarity rating. And then what you can see here is that our prior weight is also informed by clinical scores. So we can basically investigate how much impact a schizotypy score or any kind of other clinical score would have on that prior weight in order to move it either to the sensory or to the prior knowledge. The way we implemented this was in a Bayesian linear regression formula. So here you can see our prior weight, and then it's our different parameters from our paradigm. And then this prior weight is basically one part of our Bayesian belief updating model. So what you can see here is just a standard Bayesian belief updating formula. We have our posterior probability of the word that was perceived, and this is basically the sum of our prior probability of the prediction, which is basically measured by the close probability of the word that was uttered. So the close probability describes the probability with which a word was expected at the end of a sentence, and our weighted prediction error term. So this is our prior nu that I already explained to you, and then this is the standard prediction error. The only difference here is basically that because we don't have a direct access to the actual prediction, so we never asked individuals what they expected in a sentence. We're taking the different, so here we're taking whether the word is correct or incorrect in order to define our prediction error. And then what we've done is we first tested this in 109 healthy individuals with schizotypal traits. And first I'm going to walk you through a few performance measures because it's a novel task, and so we just need to see whether all of our manipulations actually worked. So what you see here is the performance across different entropy conditions. Even though we measured it continuously, we basically binned it just to make it a bit more understandable. So you can see here, this is a low entropy condition, so high predictability, and what you can see is always correct responses first, then task-based hallucinations, and no responses. And what you basically see is that the number of correct responses decreases with entropy and surprisal increasing. So you can see that the less predictable it becomes, the fewer correct responses people have, and the more task-based hallucinations. So basically, the less predictable a sentence, the more people hear what they actually expected. Does that make sense? And this is especially true in this last condition, where basically we're presenting a highly predictable sentence, but we're using a word that is mismatching with the expectation. So that's an additional manipulation. So we're presenting something like lemon, while you would expect sugar. And then people, especially in those conditions that are highly degraded, they hear what they expected rather than what we're actually presenting. And that's quite nice because we can illustrate these task-based hallucinations. And so this is exactly what we're seeing, that the number of task-based hallucination increases with entropy and surprise are increasing. Then let's have a look at how our noise manipulation works. So here, again, over those four conditions, we can see very nicely that basically higher clarity rating is provided with more channels, which is exactly what we wanted. But at the same time, you can see a kind of downwards trend. So you can see that when a sentence is highly predictable, this clarity rating is a bit stronger. So this is our indirect measure of, or our indirect effect of the predictability. So when something is predictable, people rate the clarity a little bit more. You can see that especially when you compare the low entropy condition with the low entropy mismatch condition. So that's quite nice. So what is our effect on, with regard to the schizotypal traits? What we can see is that with schizotypy increasing, people have higher clarity ratings. That is super interesting because it basically shows us already, or gives us a hint, that people who have higher schizotypal traits additionally overrate the clarity. That might be a sensory effect, but since we already saw in the display before that there is this indirect predictability effect, it could also be that they overrate the predictability or rely more on their prior.
Is that just for the correct responses, or is that
This is across all.
Because I wonder, if you split it.
Yeah, so if we split it, you can see in all conditions the same, and it's the strongest for the mismatch and the high entropy. So when sentences are less predictable, actually, so then they seem to have. So the differences between the groups, you can also see that later in the patient, is less strong for low entropy match conditions. So when everybody has a very strong prediction and you just rely on that. It's only when the uncertainty becomes stronger that you see that prediction effect.
So they overconfident on the less.
Yeah. And then what we see, there's also a weak relationship between SPQ and the number of task-based hallucination, which is quite nice. So now let's look at our modeling results. This is not a super nice plot. There will be better plots afterwards, but here it's quite neatly visible, and I will show you how to read this plot. So what we have is basically the first level is the impact of each of our parameters on our prior weight. So you can read off the prior weight down here. This is the sensory evidence, prior belief, and you need to see everything in relation to the zero. So that's basically where sensory evidence and prior weight can be separated. And then down here, everything from when you see the interaction of SPQ, you can basically see the direct effect of SPQ on each one of our intercept, but also the different parameters that we put into our model. The intercept, just like in a normal regression analysis, is basically when we keep all the other parameters static, and what you can see is that our measure is significantly different from zero. So here we can see that there is a significant impact of SPQ on the prior weight, which shifts it towards the prior belief, and we can put that in a bit more understandable and a quantitative expression, so to say. And what that means is basically when our SPQ score increases by 1 point, we see a 3.5% increase of the prior weight. So by 3.5%, our prior weight will move towards the prior. So that's a pretty strong effect. But this is when we keep all the other parameters, when we set all the other parameters to zero. So what happens if we basically simulate the data and look into a task average trial? So a task average trial would be a medium predictable sentence with a medium clarity and so on. So what we can see here, if we simulate that across the whole range of SPQ scores, which is from 1 to 70, you see a nice increase, which is exactly what you've seen before. However, if you look at the prior weight at the midpoint, you can basically see that most of the part relies more on the sensory evidence, which also makes sense if you think about a situation that is where sentences are, that this average trial is not very predictable. So a healthy person would just rely more on the sensory information. So what we did is we looked into different conditions. So here, if you have the situation where you have low entropy, so high predictability, and no surprise, you can again see the increase or the movement towards the prior belief, but it's not really crossing. So they're still relying more on the sensory information. However, if you look at low entropy and high surprisal, then people with higher schizotypal traits rely much more on the prior belief. And that does make sense because here uncertainty is really high. And so we do see this effect, and this effect is basically the same if we look at sentences that have a high entropy, so a low predictability. We then wanted to understand, whether we can relate that to prediction error processing. So we had a subset of these 199 individuals doing EEG while they were conducting the experiment. And I will only very briefly dive into the EEG results. So here we looked at the N for 100 effect, which is basically a semantic prediction error effect. We looked only at correct responses and only compared exactly the comparison that I showed you just now. So low entropy versus low entropy mismatch. And what you can basically see is the different conditions here of the sentences, low entropy to low entropy mismatch. And we use these centroparietal electrodes and the usual time window from 300 to 500 milliseconds. And then in order to analyze our results, because we had these multiple factors and especially also SPQ, we used mixed models to analyze the effect. And we looked at entropy for fixed effects, entropy, SPQ, and the interaction, and random intercepts where participants and electrode position. And then what we found basically was that the N for 100 amplitude was manipulated by condition. So the more unpredictable the context, the higher or the more negative was the amplitude. So here we can see a very nice prediction error signal. But interestingly, we found in this interaction term, we basically saw that the prediction error signal in people with higher schizotypal traits was smaller. So this is quite nice because it basically potentially shows you that they rely more on the prior knowledge. And because they rely more on the prior knowledge, even in this comparison, they have a smaller prediction error. So they still potentially have this, it's still the situation, even these comparisons, that they do rely more on their prior. So that was quite nice. However, here we haven't done any trial-by-trial analyses, which is basically the next step, to look into how the prior weight on each trial impacts the N for 100 results. Then, as a next step, also in these 55 individuals, we wanted to understand the relationship between cortical glutamate and the prior weight, because there are these theories that especially the levels of glutamate basically impact the availability of the prior or the access to the prior knowledge versus then dopamine would link to the sensory evidence. However, we don't have any, unfortunately, we don't have any dopamine measures, but at least glutamate. So we measured glutamate in these 55 individuals in 3 spots. So in the ACC, and then the dorsolateral prefrontal cortex left and right. We chose these regions because those are the regions where we find the most effects generally in psychosis in these regions. So they are not specifically for language processing. They are prediction error related, but it's mainly the regions are based on findings in psychosis where glutamate differences have been detected. And here what you can basically see here is the overlap of the voxel across the 55 individuals. As you can see, there is one outlier. But yeah, it didn't impact the results. And then we used a linear regression just to see to investigate the effect of our 3 glutamate measures on our prior weight. We controlled it for sex because we do see differences with regard to sex for glutamate. And what you can basically see is that there is a significant effect of glutamate levels in the anterior cingulate cortex on the prior weight. So basically we see that higher levels of ACC glutamate are linked to an increase in prior weight in those individuals who have higher schizotypal traits, which is quite nice. However, if you know the glutamate literature, there are very diverse findings, whether you see more glutamate, less glutamate in people with schizotypy. So yeah, but this is still a very nice indication of the contribution of glutamate to prior weight. So just as an interim summary, we found higher schizotypy was linked to higher perceived clarity, which is this indirect measure of the overweighting of the prior or the predictability. Then we saw that higher schizotypy was linked to more task-based hallucination, and we saw this smaller prediction error effect in individuals with schizotypy, but mainly in these unpredictable contexts, so when related to uncertainty. And what was basically very nice was that we had this directly quantifiable estimate of the prior weight that we extracted from our computational model, and there we saw directly that the prior weight shifted towards the prior belief and away from the sensory evidence. And this was linked to higher glutamate in the ACC. And now we wanted to understand what happens to the prior weight when we look into people with schizophrenia at different stages. So here you have the symptom progression of within schizophrenia, so you can see that the positive symptoms fluctuate, and you have basically episodes of psychotic symptoms, and then so when psychotic positive symptoms are high, and then you have these phases of remission where positive symptoms drop and negative symptoms stay relatively stable. So what we expected was that in a psychotic state, so when positive symptoms are high, we expected people to rely more on the prior weight. And then we expected that when they are in a state of remission, then this over-reliance would normalize. And so we conducted, and we are still conducting, a longitudinal study which covers exactly those relapse and remission phases. So at the moment we have 22 subjects, patients in time point 1, and 11 of those patients have already reached the state of remission, and we have controls, also not that many. Oh, I haven't updated this down here, so let's go to this. Yeah, so here it's updated, so we have 16 controls and 12 controls in the second time point. So the cohorts are still not quite big, so you need to take all of the results with some caution. But what you can see here is basically that in the psychotic phase, we have pretty strong symptoms, and those not normalized, but decrease in the state of remission. And this is especially true for the positive symptoms. So now we're going through similar plots as before. So here's our effect of noise manipulation. These are the controls. What becomes apparent straight away is that both time points are pretty similar. And you can see again this that higher clarity is provided with more channels, and that clarity decreases with entropy and surpriser increasing. So this is basically a very nice replication of the previous study. And then in the patients, you can see that the pattern is quite similar, however there's much more variance. And especially what becomes apparent in time point 1 is that especially in the very low channel representations, people present the clarity which much higher clarity ratings, which already shows that, or indicates that they very much rely on that prior in order to, or maybe that's the reason why that they overperceive, or they perceive the clarity more strongly. Then what is interesting, and again similar to what we found in the previous study, is that we see this positive relationship between Hans positive at the first time point and the clarity rating. So this is very similar to what we've seen with schizotypy. And we see that this kind of normalizes at the second time point. However, this is very preliminary because it's only 11 participants at the moment. Then, if we look at the performance, that is again the plot that shows correct words, task-based hallucinations and non-words, time point 1, time point 2, and then green controls and orange patients. What you can see is, and this is across all conditions, so what you can see here, this is the most interesting, that it looks like that patients produce more task-based hallucinations. At least they have much more variance. However, I didn't conduct any statistical analyses because the sample is just not complete yet. And we see that this potentially normalizes during the second stage. So now let's come to our modeling results. So we used, again, our computational model here. We didn't inform the model by the clinical score. The reason for that is simply because we don't have clinical scores in the control subjects. So we can't inform our model by that. So the prior weight has basically only, the calculation of the prior weight basically only has one level. And we looked at the interaction between, or the correlations between the number of task-based hallucinations and the prior weight. And this is, I think, a quite informative plot because it shows you, which is a completely expectable relationship. So you see how the prior weight links to the number of task-based hallucinations. And this is what you would expect, because if a person relies much more on their prior knowledge, basically hears more what he or she expects, then you would expect task-based hallucinations to go up as well. You can see that this is the same for controls and patients. However, you have that nice shift between the two. So you can see that patients are much more on the prior weight itself. So that is quite nice. How does it look when we specifically look at the 2 time points? There we basically see a general overweighting of the prior in the patients. So they're much more, this is now again simulated data for an average child. So you can see that the patients are definitely lying on the side of the prior belief. If you look at the axis here on the y-axis, but we can also see that this overweighting is normalizing to some extent in the phase of remission. Okay, so let me come to an overall summary now. We have, we saw in acute psychosis that higher positive symptoms were related to higher perceived clarity, and this was similar in the schizotypal traits group. And it's also an indirect sign of this overweighting of the prior, which, at least for the patients, normalizes during remission. We then saw a first indication for patients with acute psychosis producing more task-based hallucinations. Again, that was similar with higher schizotypal traits. But most importantly, again, we had this quantified evidence for the overweighting of the prior belief in stages of higher schizotypy, but also in the psychotic state. And so basically what we saw is that the prior weight shifts towards the prior belief and away from the sensory evidence during these stages of increased schizotypy or psychotic symptoms. And with that, and obviously this provides some mechanistic evidence for that is underlying these psychotic symptoms. And with that, I would like to thank you, obviously, and then the lab members that are involved in this study, and my collaborators and colleagues from Munich that are contributing. Thank you.